So, we just see here that we can do Bragg's law in reciprocal space, the way in which the number of reflections appear. So, it is always a wonder in many cases that how come when we start rotating the crystal we get more and more reflections, and this particular construction helps us to understand how this really happens and how we can get to the diffraction condition. One of the major requirements is that the scattering angle depends on the length of h, which is 2 sin theta by lambda. So, this is a major factor which we should remember. So, as the theta angle changes, the length of h will change, and since length of h will change, whenever it satisfies 1 by DHKL in this particular unit cell. So, you have a unit cell, you have ABC alpha beta gamma, and then you have the d values calculated from ABC alpha beta gamma. So, those d values 1 over d of HKL, whenever that is equated, you will get a reflection. So, this now therefore can be actually shown in such a way that as we rotate the crystal, different parts of these limiting sphere points, they will all come and intersect with the Ewald sphere, and whenever the intersection is with the Ewald sphere, whenever the intersection is on the surface of the Ewald sphere, you will get to the satisfaction of Bragg's law, and that is why our diffraction pattern is now looking like this. We get a series of spots, and these spots therefore have an identity now. The identity is with respect to the scattering angle, and the scattering angle now decides the value of h, and h is 2 sin theta by lambda. So, we can therefore index these spots in terms of 1 by DHKL, which we of course can be calling it as d star of HKL. So, we have therefore d in the real space, that is the spacing between planes. Now, it gets represented as an identity of a reciprocal lattice point, and that reciprocal point will now represent the d star or 1 by d of HKL in the reciprocal space. Right. Now, we have got to an understanding of this. We will now have to see how these spots appear. What is it that is making the spots to appear, and why one should be strong, one should be weak, and so on. Most of us have seen the single crystal diffraction spots or the single crystal diffraction pictures, and if you go to a diffractometer, you will see that being recorded on the CCD camera, where you will see them as spots. Now, the spots can be of different intensities, one is strong, another is weak, something else is hardly visible, and so on, even though the geometry is defined. In other words, the 1 over d of HKL is defined once you have A star, B star, C star, the reciprocal lattice vectors. Once you have ABC, you have A star, B star, C star. So, you have 1 over d of HKL, which is the collection of d star values. So, we know where the positions of d star will come depending upon the Bragg's law, but whether the d star value which has come at that particular point has an intensity or not depends upon what is it that is actually causing this diffraction. And this now I will take you through an exercise where we now understand what is it that is giving us this diffraction. What is it that is giving us the diffraction? It is the interaction between the X-ray beam and the electron density that is associated with that particular position x, y, z in real space. Let me repeat, the position of the atom, therefore, the atom now is consisting of electrons as we know. So, it is the electron density which is associated with a point x, y, z, which is responsible for the X-rays to do the diffraction. However, the d of HKL, the 1 over d of HKL in particular, that is the positions where the reciprocal lattice point should appear, is a geometrical calculation. So, because it depends only upon the A star, B star, C star values. So, geometrically we can identify the positions where the diffraction should occur. However, the intensity of that depends upon how much of electron density that can be associated with that reciprocal lattice point. So, if the reciprocal lattice point is now associated with a large amount of electron density, then you will get the diffraction pattern. Let me draw a little picture to show you what I mean. Suppose there is electron density something like this region where there is a lot of electron density. and this now lies on a plane which is passing through that like that. So, this could be one plane, it could be another plane, there may be another plane going like that, another plane which is going through this, and all these planes now contain this electron density. So, if you now calculate the intensity, or if you see now where these spots should come, it is already defined by geometry, but the intensity that is associated with the diffraction, or in other words the energy that comes out after scattering depends upon how much of electron density is associated with them. So, these three planes, all these three planes will have a large value for the intensity. That means these will be brighter spots compared to the other weaker spots. So, if that is the logic that is to be followed, we have to find out how this is all happening. It is all happening because the amplitude of the wave, which comes at very long distances at r, let me go back to the other mode. The amplitude of the wave at a distance r, which is very far away in terms of the lambda value, if the amplitude a of that lambda wavelength is incident on the electron with a mass m and a charge e, then the amplitude will be this value. This depends upon an expression of this kind. We have to understand what it all means. So, you have an electron with a charge e and a mass m. Now, this one particular, there is no one single electron, there are several electrons in the unit cell, right, we are associated with the molecule, atom position and so on. So, the charge is E and the mass is m. The amplitude A, that A naught, which we would like to have from the incident radiation, is already known to us. So, the incident X radiation has an amplitude A0. It gets modified after scattering, and we observe this amplitude of the wave at a sufficiently large distance. R is very much greater than lambda. Remember, I am using this vector r to identify that we are observing this amplitude corresponding to the vector r, which is the scattering vector, which can be replacing in a single crystal by the capital H, which is our scattering vector, which is essentially 2 sin theta by lambda. So, it has to satisfy the Bragg condition. So, since it satisfies the Bragg condition, we get the spot. The amplitude of that spot depends on this quantity, and this particular quantity is now A, which is the incoming amplitude, divided by r. So, if you just send an X-ray beam, the light intensity, for example, light coming from a source in front of us. So, the light will be becoming weaker and weaker as we go to very large distances. In fact, it varies as the square of the distance. So, therefore, when we take it at a very large distance, anyway the amplitude gets reduced by that particular amount proportional to 1 over r. So, amplitude is already reduced. The fact that it is the electron which is involved in the scattering, we have this E square by mc square factor coming in, and then this factor 1 plus cos squared 2 theta divided by 2, where 2 theta is the scattering angle. You see, this is very crucial. This 2 theta scattering angle decides where your H vector should come, and therefore, this factor is the one which modifies the amplitude, and therefore, you will get different intensities at different positions. So, we therefore have the amplitude of the value equal to this. Now, what is it that is causing this amplitude? It is causing, what is the electron density, right, and the electron density in our case, when we discuss atoms and molecules and collection of molecules in a unit cell, depend upon with what atom these electrons are associated with it. Suppose we have a structure which has a carbon, nitrogen, oxygen on one hand, or a structure with germanium or even higher elements like zirconium, or for that matter even uranium containing compound. So, the electron density associated with these atoms, there is a certain size of these atoms, which of course is quantum mechanically calculatable. So, this quantity is also coming from the quantum mechanics evaluation. So, we are not going into the detail of it. However, it depends upon a factor which is now going to be very, very crucial for our calculations, and that we call it as the atomic scattering factor. So, if there is a carbon atom will have 6 electrons. So, at the scattering angle 0, all these 6 electrons will contribute. So, it is equal to the atomic number. So, if the scattering angle is 0 and the carbon atom is situated there, all the electrons will contribute to that one, and therefore, it is proportional to 6. I am using the word proportional to 6 because it depends upon where you define your 0 in your crystal system, where is your reciprocal lattice origin. You saw it in the previous diagram, it is variable, we can decide where the origin is depending upon where we would like to take the reciprocal lattice point origin. And therefore, the atomic scattering factor is proportional to Z, the atomic number. So, depending upon what is the size of that particular atom, whether it is carbon or bromine or whatever, the number of electrons associated with that particular point will be proportional to Z. But it so happens that it also varies with respect to sin theta by lambda, in other words it varies with respect to the scattering angle. We already have the amplitude variability shown here for a free electron. Now, the amplitude variability is now to be shown for electrons which are associated with the atom. So, we have a position of the atom, we have the core of the atom, we have the surrounding valence electrons and so on, but they are now associated with the atom, and therefore, we have to define the atomic scattering factor in a proper way, and this is the definition. Amplitude scattered by an atom in a particular direction, the amplitude scattered by a free classical electron in the same direction. So, you consider a free electron and consider the collection of electrons associated with that atom, and then the atomic scattering factor is the amplitude that is scattered. So, what happens therefore is, if this is the free electron component, we multiply it by the factor f, which is known as the atomic scattering factor. So, this is the amplitude of the X radiation scattered by an atom. It is, as I said, ideally Z, because all the electrons should contribute. If you just put one atom and send an X-ray beam, and this particular atom is now in a position like this where the scattering angle is not seen 0, then we will see that the amplitude of the X-ray scattered by the atom is proportional and in fact more or less equal to Z. Ideally it is Z, it will never happen, because atoms are all in different positions with respect to some reciprocal lattice origin, and therefore, this value you see depends upon this 2 theta value. So, since this depends upon the 2 theta value, we see that it depends on the scattering angle. So, since it depends on the scattering angle, the scattering direction has to be considered very seriously, and that is shown in the diagram below. We will try to understand this diagram carefully, because this is going to tell us that unfortunately for us this is a limiting step for us. If it were to be individual atoms contributing their entire proportional to Z contribution, then there would have been no problem. In fact, that is what happens in the case of a neutron diffraction. We will worry about it later. But at this particular moment, since X-rays interact with electrons and there is a size of the electron cloud around a given atom, and different atoms have different sizes, different contents of electrons and so on, this particular quantity f will also vary with respect to the angle, the scattering angle. An illustration of this kind tells us that if it is not changing the direction, if it is coming in and we find electron density at this point A and electron density at this point B, it is not changing any direction going through, that means there is no change in the path. The path simply goes through, but we do find the electron density in its path. That means if this is the atom, all the electrons, effectively I have considered two small elements of electron density, but there is electron density in the entire sphere which is shown here, and all these electron density will now be a part and parcel of scattering, and therefore, there is no path difference. So, dA minus BC, dA minus BC is equal to 0. So, there is no path difference. So, if there is no path difference, there is no phase difference, phi is also 0, and as a consequence the scattering that is coming out from this atom is proportional to the value of Z. In fact, it is equal to Z at ideally 0 value of no change. But as we increase or change the scattering direction, we see that as we rotate the crystal, different parts of the reciprocal lattice will come, and therefore, the angle has to change, and that angle changes behaving the Bragg's condition. So, as the angle changes, if the angles are very small, as is shown here in the second diagram, which is referred to as B, then it's, if the angle is small like 2 theta indicated here, is a small change. So, the X rays are coming here, falling on these two electron densities, and this electron density now decides to diffract the beam. So, it follows the Bragg's law, and then therefore, this angle 2 theta comes into picture, and this will be now the scattering vector wave front. So, this yes, the scattered wave will go in this direction. So, if that is the case, then we see that there is a path difference which comes in, and this path difference dA minus BC will be equal to delta, which is the path difference if 2 theta is small. So, for smaller 2 theta values, it goes as dA minus BC. But remember that the scattering can be in all possible directions, all 360 degrees it can scatter, we do not know, right. So, when it goes to very high angles, what is happening is when you have to take a incoming radiation with a certain intensity and want to deviate that particular incoming radiation by a very large value 2 theta as is indicated here, obviously most of the intensity that is contained in the incoming beam will be absorbed by this atom. So, as a result the path difference now will become dA plus AC. So, the path difference is very large, and for 2 theta values large, the path difference delta becomes very large, and therefore, you get a very interesting behavior of the variation of f with respect to the scattering angle, and the next view graph shows you how it varies. So, we have therefore plotting here the atomic scattering factor f and its variability with the sin theta by lambda, because we would like to say see this independent of the wavelength which we are going to use. So, we show the sin theta values and we show the sin theta by lambda, so that it is a universally valid curve for all wavelengths which we can use. So, f versus sin theta by lambda now varies in this particular fashion. There are certain things which are associated with this plot which I will discuss as well, but at this moment you see that the atomic scattering factor f falls off with respect to sin theta by lambda. So, it is falling off with respect to sin theta by lambda, and at very large values it is becoming very small. So, if you look at actually a diffraction pattern, you will observe it, whether it is a powder diffraction pattern or a single crystal X-ray diffraction pattern. As you go in the 2 theta direction to higher and higher angles, the intensity keeps falling very rapidly. In fact, in an organic molecule, if you record a powder diffraction pattern, you hardly see anything at room temperature, of course, you hardly see anything beyond 35 degrees in 2 theta. That is because these values will go down very fast. You see here what is plotted is that of chlorine ion and cesium ion. I have plotted the scattering factors of ions, and as a result the cesium is getting 54 and the chlorine is getting 18. That means one extra electron added to chlorine and one extra electron removed from cesium, and therefore we get this scattering curve. So, what it also tells us is that we can represent also ionized atom positions with respect to the scattering behavior. So, whether it is in the neutral position or in an ionized position, depending upon the level of ionization, we can actually have the value of f diffract. So, for chlorine the curve will start from 17 at 0 value and then fall off exactly like whatever it is shown here. Similarly, in the case of cesium, I have taken cesium and chlorine specifically because we are going to discuss more of cesium and chlorine in the coming slides, and that is why I have taken cesium chlorine, but it is there for universally for all the elements. Now, the only problem with hydrogen is that it does not have a core. There is only one electron associated with the hydrogen, and therefore, the variation with sin theta by lambda with respect to that is hard to calculate. In fact, these calculations are done, as I have mentioned here, the values of f at various intervals along the sin theta by lambda are calculated from quantum mechanics. So, we make use of quantum mechanical methodology to calculate the values of every value. That means, we go in intervals of let us say 0.02 and calculate the values of how the f value varies with respect to the scattering angle. So, it will fall off with respect to that and comes down fairly rapidly, and then more or less stabilizes at higher angles. This kind of a scattering factor behavior is there for all the elements, and it so happens that in case of anions, we have the loosely packed electrons in anions are loosely packed than in the case of cations. So, for example, in the case of chlorine, you see that the fall off is very, very rapid. That means it starts losing the electrons at lower sin theta by lambda angle compared to the cesium, which falls slowly. So, whenever you have an anion and a cation, the behavior of the scattering factor is different from each other. The electrons in anions are loosely packed than cations. So, the fall off with respect to sin theta by lambda is dependent upon how tightly the electrons are packed in a given atom. So, all these the values of the f versus sin theta by lambda at intervals of whatever range we would like to have can be calculated from quantum mechanics, and that is not the job of this particular course. So, what we will say is we have taken that value to be already available. So, f varies with respect to sin theta by lambda. So, at sufficiently large angles, as we see, the intensities fall. The intensities fall not because the atoms are not there, but the intensity that is associated with the scattering is falling. So, they become poorer and poorer scatterers as we go higher and higher in the scattering angle, and this is a very serious issue as far as X-ray diffraction is concerned. So, as I mentioned already, hydrogen has no core, so it cannot be determined generally by a routine X-ray measurement. We have to do some tricks to identify the positions of hydrogen. When we really look at the structure determination protocols, we will actually go there and try to see how these analysis can be done. So, to just to summarize the last two slides, we now see that the amplitude of the wave is a function which is dependent upon the so called atomic scattering factor. It also depends upon what is the scattering angle, and it so happens that the atomic scattering factor, depending upon the angle of the scattering, will vary with respect to sin theta by lambda, and that variation with respect to sin theta by lambda has been indicated here. I have taken cesium and chlorine. I keep this in mind because we are going to use this for a discussion in a few minutes after this discussion. Now, we go to a situation. You see, the thing is, now we have discussed two issues. This is very important point. The scattering is done by electrons. We have a crystal, it is filled with atoms and molecules and so on. The scattering is done by electrons, and then we do a diffraction experiment. From what we see from the geometry of the diffraction, which we have analyzed already in terms of the reciprocal lattice, each and every spot we get is from a plane in the crystal. So, the diffraction is happening, the measurements are with respect to a plane in the crystal, whereas the atoms may or may not lie with respect to a plane. It is not necessary that the atoms should be associated with a plane. It is certainly not necessary that the atoms should be associated with lattice points. In fact, that is how we have been introduced to the subject in school days. That is because it so happens that if we take simple atoms, by simple atom I mean let us say copper or gold or silver or something like that. These atoms are indeed associated with lattice points in their unit cells. So, when you crystallize an atom, the crystals of the atom will have lattice points associated with them to be the positions for the atoms as well. So, that means that the phase associated with that diffraction which comes with the atom position is 0. So, it so happens that the belief that lattice points should have atoms has continued in our minds. So, we have to give away that belief. What we measure in a diffraction experiment is a measurement which comes as a consequence of Bragg's diffraction, which is occurring from a plane in the crystal, and we know how to identify planes, we know how to identify those as reciprocal lattice points, we know the geometry. The geometry is done by the Laue conditions and also by the Bragg's equation. So, it is not a continuous distribution, it is certain set of regions where the angle, the scattering angle corresponds to the length of the reciprocal lattice vector. Whenever that happens, we get the diffraction. So, we have these diffraction points, those are coming from planes. The diffraction is coming from the planes in the crystal, and therefore, it is single spots bright and dark and so on. We now just analyzed why some are bright and some are dark, depending upon the amount of electron density that is present associated with the atom. Now, the atom goes and sits in the unit cell in some position x1, y1, z1, x2, y2, z2 and so on. Now, this x, y, z is not necessarily to be associated with a lattice point, or for that matter any point that can occur inside the unit cell is a possibility of an atom to sit there. The only thing which will also have to be obeyed is the fact that it has to obey the symmetry rules we have made. That means, if it is sitting in a monoclinic system, it has to have a minimum two-fold symmetry with which it generates the other atoms. So, if there is an atom at x, y, z with a two-fold symmetry P2 space group, you know that x, y, z should generate x bar, y, z bar. That part we know. So, that means there are two of those atoms inside the unit cell at x, y, z and x bar, y, z bar. So, both these atoms now will contribute. Now, both these atoms will contribute to every reflection which is satisfying the requirement that the scattering angle should be equal to the length of the reciprocal lattice vector. So, if that is the logic, then how do we get the atom positions? So, this is an issue which we will address hereafter, because what we are measuring from the diffraction experiment is the reciprocal lattice geometry, by means of which we identify the individual h, k, l values, the so called reciprocal lattice vectors h, k and l, and we also measure the intensity that is associated with a given h, k, l. So, when you have a crystal in an X-ray beam, the X-ray beam passes through the crystal, diffraction occurs and you will get various spots, and these spots now can be identified with a certain h, k, l. We also can measure the intensity that is associated with it experimentally, and that intensity is the one which is associated with that lattice plane. Now, the requirement that atom should be there or not is not there in this entire experiment. The atoms can be at some point in space which is defined as x, y, z, or x1, y1, z1, x2, y2, z2 depending on the number of atoms, and therefore, this issue has to be completely understood, and how a position x, y, z contributes to a h, k, l reflection has to be evaluated, and we are now planning to look at that particular phenomena in more detail. In order to do that, we need to see the way in which the planes are oriented in a crystal. We are quite familiar with this now. We can draw a diagram of this kind, or we can draw a diagram with respect to reciprocal lattice points. But I think in direct space we have still a very clear picture, because it is always better to have a direct space geometry, and therefore, we are drawing this particular diagram. Now, this diagram tells you that there is a plane which passes through the origin 0, 0, 0. Now, in the previous class we learnt that any point along this particular direction will scatter exactly the same way. So, suppose there is an atom sitting at 0, 0, 0, and then I put an atom at this position which is moved along this direction with the plane, within the plane. So, the plane, now you remember, plane is a two-dimensional thing which is coming out towards us. So, any of these points lying with respect to the origin 0, 0, 0, they will all scatter in a phase. So, suppose there are 10 atoms in this particular plane, all the 10 atoms will scatter in phase. 5 the scattering angle, the phase associated with this will be 0, and because there is no difference in the path. The path length is 0, path difference as we saw in the previous slide, and therefore, we have delta 0 and phi 0. So, 0, 0, 0, if there is an atom here, it will now contribute its entire scattering power to this particular plane. So, this plane could be some HKL associated with 0, 0, 0, and this the first plane away from the origin. Now, if you consider the first plane away from the origin, it has to satisfy the Bragg condition, and what is the Bragg condition? 2d sin theta is lambda. So, the path difference should be lambda. So, from the origin, every diffraction plane which will come will be a path difference or multiple of path difference associated with d of HK. We have seen that it depends upon the value of n lambda. N could be 1, 2, 3, 4, 5, 6 to whatever. So, if we consider n is equal to 1, then the path difference is then delta equals lambda, and the corresponding phase change will be 2 pi. How is that coming? The delta path difference is delta is the path difference, the phase difference is 2 pi. You go back to the discussion where we had the how the path length and the phase they come with respect to each other, delta r going to r plus delta r, and that gave a path difference, and that delta r now gets multiplied by a factor of 2 pi in order to get the phase difference, which is a reduction in the phase. So, addition of a longer path length will reduce the corresponding phase, and therefore, we get a phase difference which is 2 times pi. So, if delta is lambda by 2, then we get a phase value of pi. Now, how does that happen? It cannot happen here, but suppose it can happen, then we will have to remember that delta can be then lambda by 2. Keep that in mind, we will solve that mystery in a few minutes. So, if delta is lambda by 2, then phi will be equal to pi, remember that, and so on. I mean, if delta is lambda by 3, lambda by 4, etc. Now, under what circumstances we will have that kind of a phase contribution to the given crystal, because at this moment we do not have any such contribution. By definition, the first plane out of the origin plane, the plane passing through the origin, must have a path difference of lambda by Bragg's law, and therefore, since Bragg's law says it is the only way in which we can have this particular plane, which is now at a distance of d of HKL, will give us the diffraction. The next path which we will next plane we will get will be the 2d HKL. There the delta is 2 lambda, phi is 4 pi. So, these numbers have to be now integers. We can of course go in the negative direction as well. We can go up from the 0 0 0 plane, and we get a phase difference which is minus 2 pi. Again, the value of delta is lambda, it is moved by d of HKL, but since it is in the opposite direction, the phase change will be minus 2 pi. Now, what is 2 pi? 2 pi is 2 times the pi value. What is pi? What is 2 pi? 2 pi is 360 degrees, is it, or 180 degrees, which is correct? Think about it. We will leave you at this particular point, and then once you tell me what is 2 pi, we will go further, or once you realize what is 2 pi, we will go further along.